Hey guys, Dr. Viz here. I am going to go over the homework problems from chapter 12. I seem to be having some issues with my screen recording software and Microsoft Word, so I'm going to be doing this in a PowerPoint with each problem on its own slide. So before I get started, I just want to point out that my numbers may be different from yours. ChemVantage makes things random with the numbers it puts out for everyone for their problem, but the work through should be the same. So let's go ahead and start off with number 1. So we're told at 500 Kelvin, the half-life for the isomerization reaction, that is 1,000 seconds. The activation energy is known to be 160.7 kilojoules per mole, and we want to predict the half-life of the reaction at 508 Kelvin. So let's use a different color. There we go. Let's do this nice blue. So let's start off by writing down what we know. We know that we have this initial temperature of 500 Kelvin. And at this temperature, it has a half-life. I'm just going to go ahead and call this T1 of 1,000 seconds. I have a second temperature of 508 Kelvin, and I want to know what its half-life is, that I'm calling T2. I know for both of these, the activation energy is 160.7 kilojoules per mole. And we can go ahead and just rewrite that as 160.7 times 10 to the third joules per mole, because there's 1,000 joules per 1 kilojoule. And we need this in joules for our equation. So I think the hardest part here is actually figuring out what to do with our equation. So we know that the natural log of K1 over K2 is equal to our activation energy divided by R times 1 over T2 minus 1 over T1. We know everything except we don't know K1 over K2. We don't know either of these. We don't know their ratio. But one thing that we do know from our half-life equations is no matter what our rate law is, our half-life is inversely proportional to the constant, to the K, for our rate. So we can use this to our advantage and go ahead and say, okay, I'm going to rewrite this and say T1 over T2. And since T1 is proportional to 1 over K1, T2 then is proportional to 1 over K2. And we can rewrite that then as K2 over K1. And one thing that we also know is the proportionality constant, it's going to be the same. So if these were called these X or something, they're going to cancel out. So we can also say that the ratio of T1 to T2 is equal to the ratio of K2 to K1. In our equation, though, we have it's opposite. So then that means to rewrite this, K1 over K2 is equal to T2 over T1. So now we can take this T2 over T1 and substitute it in for K1 over K2. So now let's go ahead and start plugging and chugging. I'm just going to, for now, write this as T2 over T1. Even though we know T1, I'm just going to do that for now and focus on the right side. We know our activation energy is 160.7 times 10 to the third joules per mole. And we're dividing that by R, which is 8.314 joules per mole times Kelvin. So we can see joules and moles cancel, times 1 over T2, which is 508, minus 1 over T1, which is 500. So this simplifies down. Now we can say of 19,329, and the units of this are Kelvin, from doing EA over R, times 1 over 508 is 0.001969, minus 1 over 500, 0.002, or 2000, if you want to be more exact. And the units that's in this parentheses 1 over Kelvin. So 1 over Kelvin times Kelvin, those cancel out, which makes sense. We need our natural log to be unitless. So now this is the natural log of T2 over T1, and that's equal to negative 0.5992. I'm going to go ahead and write 1,000 now for T1. Now we need to get rid of the natural log. So the opposite of natural log is e. So we're going to go ahead then and take e to the power to the negative 0.5992. And that is now equal to T2 over 1,000. So then T2 is equal to 1,000 seconds times e to the negative 0.5992. And this is 549 seconds. So I think the most challenging part there was figuring out how to get rid of that K1 over K2. After that, it's pretty much plug and chug into our equation. All right. Number 2, we're given a reaction, and we are told it is second order with respect to HI, and it has a rate constant of that, and we want to compute the initial rate of reaction given a concentration of 0.0130 molar. So since we're told this is a second order reaction, then we know that the rate equation, the rate of the reaction equals K, and we're told it's second order with respect to HI. So that means we only care about the concentration of HI. Since it's second order, it's squared. We know K is equal to 30.0 inverse molar times inverse seconds. And our concentration of HI, its initial concentration, is 0.0130 molar. So we are just going to plug in these numbers for our rate. Since that's an initial concentration, that also gives us our initial rate. So this is K, which is 30.0 inverse molar inverse second times HI initial, 0.0130 molar. So we see molar, inverse molar cancel out. And so then we get a rate. Oops, I forgot to square that, sorry. So rewriting this, 0.0130 molar squared. Don't forget the square. So then that gives us, so this inverse molar will go away, and one of these molars goes away. So if I rewrite this now, we can just do it like this, 0.1030 molar. There we go. There we go. So just rewriting that so you can see the units canceling and what stays. So then this rate is 0.00507 molar times inverse second, or molar per second. So number 2, the trick was writing the rate equation based off of the information they gave you. Number 3, we're given a recombination reaction, and we're told it has a second order rate constant. And we want to find the half-life of the reaction if the initial concentration of HO2 is 4.89 times 10 to the negative 11th molar. And then they do give us a clue to tell us because the coefficient 2 is in the reaction, it changes the integrated rate law to this here. We have to account for that too with the KT term. So let's start by writing what we know. We know that K is equal to 1.3 times 10 to the 9th inverse molar inverse second. We know our initial concentration of HO2 is equal to 4.89 times 10 to the negative 11th molar. And then we know that the half-life equation for a second order reaction is equal to 1 over K times HO2 initial. But we need to add an extra part here because there's that 2 in front of HO2 in the balanced equation. we need to account for that stoichiometry, so we need to multiply this times 1/2. So that's where that 2 now becomes 1/2. So now let's go ahead and start plugging in our numbers. We have 1/k, 1.3 times 10 to the 9th inverse molar inverse second times 4.89 times 10 to the negative 11th molar. And then all this times 1/2. You can see molars cancel out. And so then this comes out to be 7.87 seconds because you have 1/1 seconds. So then that means it's seconds. So that's our half-life, is 7.87 seconds. So the trick here was adding that 1/2. They gave you a clue with the reaction, the integrated rate law, but that one was a little tricky. All right, number 4 here. We're told an unknown inorganic phosphate undergoes first-order dehydration in a drying oven. Initially, the excess water content is measured to be 1.69 milligrams. After 1.90 days, the water content is reduced to 0.654 milligrams. After 4.40 days, water content is only 0.187 milligrams. Determine the half-life of hydration under these conditions. So one thing that would help here is you can make a little table where you look at your time using it in terms of days versus your concentration of water in milligrams, or your amount of water. So we're given 3 data points. At time 0, we have 1.69 milligrams. At 2, 1.90, and 0.654 milligrams. And then 4.40 days, we have 0.187 milligrams. So we're told it's first order dehydration, which helps a lot also. So that tells us then that the T1 of a first order reaction is equal to 0.693/K. And we also know that the natural log of A0, so our initial concentration over our concentration at a certain time, is equal to KT. And then we can reorganize this a little bit because we need to solve for K here. So K is equal to 1/T times the natural log of A0 over AT. Just making that look pretty. And then we can go ahead and choose really any data point that we want here. So I went ahead in my work and I chose 0.2. You could choose 2 or 3. You can't do T1 because your time is 0 there. So then we can go ahead and use this data point. So time 1.90 times the natural log of A0, which is 1.69, divided by our amount at our time, which is 0.654. And so this gives us a K of 0.500. So now we can solve for T1 half, 0.693 divided by K, which is 0.500, and we get 1.39 days as our half-life. And the last one from chapter 12, number 5. We are told a common rule of thumb is that raising the temperature 10 degrees, for instance, from 169 to 179, doubles the rate of a reaction. We want to know the value of activation energy that makes this statement true for this particular pair of temperatures. So let's start by writing what we know. We have a T2. I'm going to use T2 since that's our second temperature is 179.0 degrees Celsius. But one thing that we know is we need to be in Kelvin. So we need to add 273 to this. So this is 452 Kelvin. We need to also do this for T1, 169 degrees Celsius, add 273, and we get 442 Kelvin. And then we also see that we're doubling the rate of the reaction. So that also tells me that the ratio of K2 to K1, since that each one of those is directly proportional to our rates. So since we're doubling the rates, we're doubling the Ks. So then we know that the natural log of K2 over K1 is equal to negative EA over R times 1 over T2 minus 1 over T1. And we know that K2 over K1 is equal to 2, so the natural log of 2 is equal to negative EA that we're solving for, divided by R, which is 8.314 joules per mole Kelvin, times 1 over T2, which is 1 over 452, minus 1 over T1, 1 over 442. And so then this simplifies down to be, negative EA times negative 0.0000 604. And that's from doing 1 over 8.314 times the inside from the temperature difference. And we see negative negative makes us positive. So we see that the natural log of 2 divided by, well, the natural log of 2, actually, we can just simplify that, is 0.6931 divided by 0.0000604 is equal to our activation energy. And this gives us 1.15 times 10 to the 5th joules per mole. But I believe ChemVantage wants our answer in terms of kilojoules. So this then becomes 115 kilojoules per mole divided by 1,000. So that does it for the chapter 12 homework. I hope this answered some questions. Remember, if you do still need some extra help, let me know. I'd be happy to assist.